we'll have to wait for a few more months. So I'm going to tell you about a program of using the Bootstrap paradigm to put constraints on theory of quantum gravity. And the program is still a little bit in its infancy. And I will put it in the context more broadly of what the Bootstrap community has achieved in the past few years, and give a couple of illustrations of the things that we have done and of the outlook for the future. So, so what is the Bootstrap? So actually I was looking this up to prepare for this colloquium. So the etymology of this famous phrase, pulling yourself up by your bootstraps, is interesting. It started, of course, as a sarcastic remark to try to say that something is truly impossible. Obviously, you cannot, it violates the laws of mechanics, of being able to lift yourself up by pulling your bootstraps. And this was in fact originally used in the American press in the late 19th century as a to mock someone who was trying to do something impossible. But it gradually became to mean that you're trying to do something which, according to Wikipedia, is a process that is self-starting. So it doesn't use much of an external input whatsoever. And it's in physics, in theoretical physics, it has come to mean using general consistency principles, very abstract symmetry principles, for example, or the very general rules of quantum mechanics, such as positive probabilities, to distinguish putative physical theories that may naively appear consistent, but truly are not, according to these very general rules, from the landscape of fully consistent theories. So, so the modern version of the Bootstrap program in theoretical physics is this very lofty goal of finding the space of all possible theories. Of course, I need to specify in which framework, and I will be more precise in a minute, what kind of, what we mean by theory. But once we postulate what are the axioms of what we mean by a certain class of physical theories, then the idea would be to find them all, classify all possible physical theories just using these consistency principles. So this sounds preposterous, and this history of the subject in theoretical physics is also interesting. It started, you know, you may recall that there was this program in the 50s and 60s, given that people were despairing of solving the theory of the strong interactions using anything like a microscopic field theoretic model. They were trying to say, okay, well, let's just try to bootstrap it using the very general principle of scattering of hadrons. And that program didn't quite work as originally intended, but it led to all sorts of beautiful developments, including string theory. And so the more successful version, I will come back to these scattering scattering processes at the end of the talk. But the more successful incarnation of the Bootstrap program is in the context of conformal field theory. So what are conformal field theories? Conformal field theories are quantum field theories, which have this very special symmetry. They are invariant under distortions of space, if we are dealing with models that describe, for example, condensed matter or statistical physics model, which are purely formulated in space, or as the case may be space-time, if you're dealing with models of particle physics. Transformations that preserve angles. So what is a conformal transformation? It's a transformation that locally looks like a rotation times a scaling. Here is an illustration of such a transformation, sending a square grid to this distorted grid. This may sound very peculiar and very special. In particular, the simplest conformal transformation is that the dilation. And so a theory which is conformal invariance in particular is invariant under redefinition of the scale length or of mass or of energy of your system. And clearly, most physical theories are not like that. So we have intrinsic mass scales and intrinsic less scales in the world. So why on earth would this be relevant for physics? But in fact, it turns out that precisely the opposite is true. Conformal field theory are absolutely central objects in physics. And here I'm illustrating three realms of physics where they play an important role. One is particle physics. Why would conformal field theory be interesting in relativistic quantum field theory? Well, because essentially, if you go at very high energies, then you can neglect the intrinsic mass scales of the system because you get to a scaling limit at very high energies. And conversely, also if you go at very low energies, the characteristic length scales of the system are not important. And so it's actually believed on very general grounds that the general quantum field theory sort of interpolates between a conformal field theory at very high energy and another conformal field theory at very low energies. Conformal field theories are also important in the theory of phase transition, and the middle picture here illustrates the phase transition between liquid and between fluid and superfluid helium, of which I will have more to say in a minute. And there, the idea is that near the second order phase transition, the system becomes scale invariant and in fact conformal invariant, and we can study the critical behavior of that phase transition, and for example, discuss physical critical exponents using the frame of a conformal field theory. And finally, also in condensed matter, quantum critical points, such as the one that are supposed to be relevant for high temperature superconductivity, are also described by conformal field theories. And the other idea is that the extra symmetry makes these theories mathematically rigid structures. And so they're prime targets for this very general approach using the bootstrap. And so what is the conformal bootstrap program? It's, again, this clearly now more concrete, because at least I'm telling you what kind of theories we're talking about, but still extremely ambitious, which is the idea of compiling a catalog of all consistent conformal field theories in various dimensions of space or space-time. And so this idea is an old idea, it goes back to the early 70s, where the axioms that such a theory should satisfy were formulated. And then a beautiful success story is the fact that on this without ever needing to write down a concrete field theoretic Lagrangian model, you can actually find exact solutions in 2 dimensions. 2-dimensional conformal symmetry is more powerful because it's infinite dimension. That's the famous story of BPZ from the early 80s. And then the modern era that starts with this beautiful paper in 2008 by Rattazzi et al. Is sort of I would say there are many reasons why the idea is recent. One is that powerful computational methods have become available on everybody's laptop. You don't have to be a proficient computational physicist to be able to run Mathematica. And the other idea that made this coming back with the bootstrap sort of timely in the modern era is that one retreats a bit from the very ambitious idea of completely finding the theory of everything or solving the theory of the strong interactions or solving a concrete theory to this other more subtle idea, which you actually just want to exclude parameter space. Conformal field theories are characterized, for example, by critical exponents. I will come back to that in a minute. And you don't necessarily want to exactly find those critical exponents, but just find exclusion plot. You want to carve out the space of possible parameters by numerical. And so the main slogan, which I will repeat over and over again during the talk, is that not anything goes. You start with a set of principles, a set of axioms, which are in sort of intention with one another. And so you have a guess for how a certain model should behave, and you have a guess for the values of these parameters. And I can feed these parameters to the Bootstrap oracle. And the Bootstrap oracle is a black box that implements certain constraints that follow from the Bootstrap axioms. And so you have your guess for what the values of those parameters should be, and the Bootstrap oracle can rule them out. So if you rule them out, then you're out of luck. You have to refine your ansatz, or perhaps the bootstrap will not rule them out, and at that point, it doesn't necessarily say they are correct, but it says, well, they could be correct. And so by this method, which can be implemented on a computer, you get to carve out the space of possible parameters. And so there are many beautiful examples of this story, especially in the context of statistical mechanics. One is the exact solution, not exact solution, well, the numerical solution, should I say, still rigorous, but using a computer, of the three-dimensional Ising model, just using these very general principles. But of course, the Ising model was already quite well known before. So I want to illustrate the story here with a more physically dramatic example, which is the phase transition to superfluid helium, which happens, of course, at very low temperature. Is this famous spike divergence of the specific heat that you observe just above 2 Kelvin between the fluid phase on the right and the superfluid phase on the left. It's a really dramatic thing to watch, actually, in a lab experiment. And famously, this divergence, which is characteristic of these phase transitions, is characterized by a physical critical exponent. So the specific heat diverges with the power alpha, which is characteristic of the phase transition, and it falls in a certain universality class. It depends on the symmetries of the system. And you can compute this critical exponent using traditional Monte Carlo methods, and you can also measure it. The measurement is very subtle because on Earth, if you have a sample of liquid helium, because of the pressure gradient due to gravity, only a very tiny layer of the sample can be at the critical point, and above and below, it's going to be above or below criticality. And so the only way to do a precise experiment is actually in space. And the experiment was done in 1992 on this space station. It's perhaps the only good thing ever to come out of the space program. And they made a very accurate measurement, with the most accurate measurement of a critical exponent in all of physics. And sadly, the experiment has a very dramatic discrepancy, 8 sigma discrepancy with Monte Carlo. So this was an outstanding tension that was there for decades. And the tension has now been resolved by the bootstrap. So I'm showing here a plot from this beautiful work of our colleagues that has been done within the framework of the Simons collaboration, the non-laboratory bootstrap that supported this project and many others. And so what the plot is showing here, so first of all, you have this three-dimensional plot. There are 3 critical exponents here. If you're familiar with the language of conformal field theory, these are the so-called scaling dimensions of the local operators of the theory. And if you recall from my previous slide, delta S is the quantity which is related to the critical exponent alpha for this characteristic divergence of the specific heat. You don't have to know what these numbers are, except that they are, this is an illustration of what I meant before by carving out theory space. So you have a theory which is a putative theory, a candidate theory, which is characterized by an infinite set of numbers. And here I'm showing a 3-dimensional slice of this infinite dimensional parameter space. And the idea is that not anything goes, not every single point of this parameter space is allowed. So in this plot, you see here, first of all, the gray region, or whatever it is, grain or brown, whatever it is in the bottom. That's the range given by the experimental results. The green area is the Monte Carlo results. So you see the very dramatic, they miss each other very dramatically. And this little tiny dark blue sliver is the Bootstrap results. So the Bootstrap oracle actually first of all, it's compatible with the Monte Carlo results. You can see it's much more precise than Monte Carlo. And so this actually resolves the discrepancy in favor of theory. So somehow the experiment is either wrong or they underestimated their errors, and it's hard to tell because, you know, not a similar experiment is not in the, hasn't been planned. But anyway, so this is the kind of thing you can do, and it illustrates the power of this very general principle. What goes in making this plot are very general axioms, such as the fact that probability are positive and the fact that the correlation function of conformal field theory have to obey certain symmetries. So I'm not really showing any of the math here, but I will give an illustration in now of a simplified setting, which will also be relevant for the rest of my talk, of what kind of Bootstrap equations are underlying this kind of exclusion plots. By the way, it goes without saying that you should interrupt me anytime if there are questions. Okay, so both because it will be important for the second half of my talk, and both because it's a simplest illustration of where these constraints are coming from. I will now specialize to a version of the Bootstrap which is specific to two-dimensional conformal field theory. So, two-dimensional means 1 + 1 dimensional. So 1 dimension of space and 1 dimension of time if we're doing a Lorentzian theory. And so if you consider the theory, first of all, in a compact space, so a circle, and if you further consider its statistical ensemble at finite temperature, so famously, a theory of finite temperature is computed by path integral, where you do the path integral over, in this case, over a torus, where you think of the time direction as Euclidean time of radius beta, where beta is the inverse temperature. And so here is a picture of a torus. And you're supposed to do the path integral over this manifold. And you write down the statistical partition function, as usual, as a sum over the energy eigenstates of the system e to the minus beta ei. I'm suppressing here possible integer degeneracies in front of, this is the sum over an entire spectrum counted with degeneracies. And now there is this very simple idea that, well, the moment you write this as a path integral over this toroidal region, who's going to tell which is space and which is time? I can flip my head and decide to invert the relation of space and time. And given that the theory is conformal, the only thing that this partition function can depend on is the ratio of the time and space directions. And so from immediately find this very important constraint that the partition function should be invariant under what is known as a modular transformation. You send beta into 1 over beta. There are really two constraints here in this simple equation. One is positivity. This z of beta is a positive sum. You know, these are the degeneracy of the states. So here the degeneracy is 1 because I'm counting, you know, I is all the states, but you know, it could be in principle any other integer, but it has to be positive. And the other one is this so-called crossing, in this case, crossing transformation. We are making a transformation that such that when on one side the parameter is going to 0 and the other side is going to infinity. And there's a certain tension between the transformation. And so that means that you really cannot satisfy this equation for an arbitrary choice of real positive numbers ei. So this simple equation puts a constraint on the allowed value of ei. And now the game will be an exclusion game. You have your favorite set of energy levels that you think might apply to your model, and I'm going to plug them in this equation and check whether or not the equation is satisfied. So this is the kind of thing you can do with the Bootstrap. It's the simplest illustration of the Bootstrap, and the idea is to carve out the space of putative energy levels EI and see what whether we can find any special features. So in practice, of course, this is not so easy, and you need to be clever. And so you rewrite this bootstrap equation as something equal to 0. And again, it's important here that this is a positive sum of this object e to the minus beta e minus e to the minus e over beta. And then in order to milk this cow, this bootstrap cow, you want to apply on it a cleverly constructed linear functional, which here is represented as taking a derivative with respect to beta at the crossing symmetric point beta equal to 1 with some cleverly chosen coefficients alpha n. And a cleverly constructed functional will distill the physical consequences that come from this bootstrap equation and give you a constraint on the possible allowed spectra EI. So that is the bootstrap game exemplified in this simplest context of the two-dimensional modular bootstrap. So just to reiterate, I call this a bootstrap equation, but clearly it's infinitely many equation. Right? This constraint needs to be satisfied for each value of beta. And then in order to process that in a clever way, you can apply the linear functional method. So okay, so that concludes my introductory first part of the talk. And now I'm going to switch gears to quantum gravity. And again, the slogan is not anything goes. In the context of quantum gravity, this has a funny name, which is the swampland program. The idea being that if you give me a randomly chosen effective field theory, by which I mean you choose a certain particle content and certain interactions, the law says that that effective field theory will not, in general, admit a fully consistent UV completion. And so if it does not admit the UV completion, we say that it's part of the swampland. And so the swampland program aims to distinguish the swamp from the good, honest, dry terrain of truly consistent theories that can admit the UV completion. In fact, in the context of the bootstrap, this is a very nice metaphor because actually, I was researching the origin of pulling yourself up by the bootstrap. I encountered the fact that the first instance of a similar metaphor is in the Adventures of the Baron de Munchausen, who actually was lifting himself up from the swamp, not by his bootstrap, but by pulling his pigtail. And so here, as an illustration, I have something like action of Einstein gravity plus higher derivative corrections plus a scalar, all sorts of possible higher derivative correction. This is the sort of effective field theory that you write at low energies. And the idea is that, well, first of all, the matter content, and second of all, the choice of these couplings should be constrained in a fully consistent theory. And so we would like to play a similar exclusion game in the context of quantum gravity. In fact, even without dynamical gravity, this game has been played for years, and there's been a story that goes back to a beautiful paper, 2006, by Dubosky, Arkani Hamed, Adams, and Nicolis, that were playing a similar positivity exclusion game of the kind that we illustrated at the very end of my talk. Now, before I get there, there is an obvious thought. Those of you who have gone, first of all, those of you who are theorists know this very well, but those of you who are not theorists and have gone to any number of colloquia in the past certainly have heard of the holographic correspondence that postulates if you look in quantum gravity in a box, in this very symmetric box, which is anti de Sitter space, the space of constant negative curvature, there is a mathematical correspondence that relates that to conformal field theory on the boundary. So here is a sketch of anti-de Sitter space in and the boundary of the anti-de Sitter space is the interior of the cylinder, and the boundary of the cylinder is as one dimension less, and the idea is that the boundary is described by conformal field theory, and the conformal field theory entirely captures the physics of the bulk gravitational theory. And here, what is sketched here is a sort of a scattering experiment where we are throwing stuff in from the boundary in the inside by perturbing this boundary surface. And so we get to describe scattering processes in the bulk in terms of correlation functions of the conformal field theory. So the first obvious thing you can try to do is to restrict to this situation where we don't quite describe gravity in asymptotic flat space, which is a good approximation of the real world. Actually, the real world is positive cosmological constant, but let's start with zero. And instead we go to this more idealized toy model where we consider negative curvature, and we study quantum gravity via the holographic duality by resorting then to conformal field theory, for which we have now well-honed Bootstrap methods. So in fact, the original hint for holography came from this famous work in the 1970s of Bekenstein and Hawking. Bekenstein originally postulated based on general thought experiments, and Hawking demonstrating using his famous calculation of the black hole radiation. The black holes, in fact, are not black. They radiate, and they behave very much like thermal objects with an entropy which scales like the area in Planck units. And so that's the first hint of holography. The number of degrees of freedom of the black hole is humongous, because at least for here I did the little, I had some fun doing the calculation for this M87 massive, supermassive black hole, which recently was more or less photographed with lots of fine print. But anyway, you can take this as some sort of a picture of the supermassive black hole in the M87 galaxy. And if you plug in the values of the radius of the event horizon of the black hole, which is 120, the distance from Earth and Sun, and you plug in the numbers, you find that this black hole has this enormous 10 to the 96 entropy, which of course just a reflection on the fact that it has an astronomical size and the Planck length is so small. But the holographic hint here is the fact that the number of degrees of freedom scales like the area, not like the volume, and that is encoded very beautifully in the ADS-CFT correspondence. Okay, so now that I told you this, that we're warm up with the general philosophy, we can try to do something a little bit more concrete. So of course, ideally, we would like to do this in 4 dimensions, which is the dimension of the space-time of the world. But that's a little hard. I will have little to say about that. I will make some comments at the end. And we can now look at a warm-up toy problem, which is to study quantum gravity in 3 dimensions, in 2+1 dimensions. 2+1 dimension, of course, is a bit of a toy model because there are no propagating gravitational waves. There's no gravitons in the bulk. But remember, we're doing gravity in a box, and it turns out that if you do a more sophisticated analysis, that actually a little bit of dynamical gravity is left, but it has to live on the boundary. So there are what you may call these little ripples of boundary gravitons in the space. And here is the action of 3D gravity with negative cosmological constant. This -1 over L square. L has units of length, and it's the characteristic curvature length of this space. And the vacuum solution here would be the space of constant negative curvature with radius of curvature L. And then here there's dots and question mark. And so yes, we want gravity, but then what else? And a question that may at first sound surprising to you is the following: could we have a theory of pure gravity? Well, in 4 dimensions, the answer is presumably no. It seems very preposterous, given that the gravitational coupling grows at a short distance. It's very likely it would not be possible to have a theory of pure gravity in 4 dimensions, and you need other degrees of freedom. In 3D, it's a borderline question, precisely because there's no propagating degrees of freedom. And the truth is, we don't really know. This is a notorious question that in theoretical physics has been open for decades. There are many wrong turns, including by famous people. And we don't know. Do we need additional degrees of freedom, such as string theory, supersymmetry, or what? And I should emphasize that what I really mean by pure gravity, it cannot just be the gravitons. That's easy to prove. One reason it's easy to prove is that you can compute, first of all, this model admits black hole solutions. And by the formula I had earlier, these black holes have an enormous amount of entropy. And so you need some degrees of freedom that account for the black hole entropy. You need some microstates that account for the black hole entropy. So the minimalistic theory you may want to have is a theory that just contains these boundary gravitons and whatever it is that makes up these very massive degrees of freedom that make up for the black hole entropy. That's what the minimum you can have. And basically, from a dimensional analysis, in the black hole entropy, we'll have to scale like the characteristic length of the space, which is L over L Planck. And this black hole will be very large if we take the Newton constant to be small, which is the case for Wiffi coupled gravity. And so this number L over G has another significance, which is of course closely related to the counting of black hole entropy. It's the measure of the number of degrees of freedom, the so-called central charge of the dual CFT. Okay, so to recap, we want to address the question of what are the possible theories of gravity in 3 dimensions, and in particular, how simple can a theory in 3 dimensions be? Can we have something like pure gravity? And we're going to address the question by appealing to the holographic correspondence and studying the question in the context of 2-dimensional conformal field theory. So this would be a good time for questions if there are any. Okay.
Well, so I have a silly question, Leonardo. It's really so lovely to be walked through this. But why isn't just a totally empty theory okay? It seems like that would always be okay.
Sorry, what? I mean, I need gravity,
especially
right?
An empty universe. Why couldn't a theory just have nothing? And then it seems like it would be consistent. And yet, right, you're talking about the theory conceptually, but am I supposed to distinguish between the theory and particular states? Maybe that's what I'm confused about.
I'm not considering states. I'm really concerned about the theory. I'm talking about the theory. So the theory will have a Hilbert space, right? And so the question is, what are the states in this Hilbert space? It's a quantum mechanical model, right? So there will be Hamiltonian, a Hilbert space, and all the whistles of quantum mechanics. And the question is, how does this Hilbert space look like? So we know there will be a vacuum. That's what you're thinking about, the empty space. But then there will be excitations about the vacuum. There are these, for example, these boundary gravitons. And the question is, what else do we need? Could we just have the vacuum and these little ripples of gravity? And that is a resounding no. It's easy to prove that that is impossible. What is the minimalistic thing you can add to the degrees of freedom of the theory such that the theory makes sense? And so to recap, so we have this correspondence that I'm really using to describe these black holes in the bulk via the boundary theory. And so black holes, as I emphasized earlier, these are thermal objects. And so they're related to the conformal field theory of finite temperature. So we are precisely in the situation that I indicated earlier, where we are studying the theory, the two-dimensional field theory at finite temperature. And so then we now have a very precise way to ask the question of what is the simplest theory of 3D gravity. Well, there will be a state of zero energy, E0 equal to 0. And then what else can we have? How high can we take the first excited state about the vacuum to be? And so here is a cartoon. So the vacuum, so this is a picture of the energy level, so the theory. So E is the energy. There's a unique vacuum which has zero energy. And then, as I told you, there are no gravitons in the bulk. Well, we have these little boundary ripples, which for those of you who know these things are actually the Virasoro excitations of the conformal field theory vacuum. But anyway, whatever they are something which has energy of order 1. And you should think of them as perturbative excitations of the empty vacuum. And then we can, precisely using the simple formula I had earlier, we know that black hole solutions have a large entropy that scales like the number of degrees of freedom C. C needs to be large for the theory to be Wilkie coupled. And the question is, how high can we take the first non-graviton excited state of energy E1 so that the theory is consistent? Can we push this E1 all the way up to the black hole threshold? That would be the theory of pure gravity. Or do we must we instead have degrees of freedom that are below the black hole threshold? This is now a very precise mathematical way to address the question of what is this landscape of three-dimensional gravity theories. But remember, not anything goes. I told you that zeta of beta has to be equal to zeta of 1 over beta. And so your proposed spectral assumption, your proposed set of energy levels, including the value of E1, has to satisfy this equation. And then it turns out that there's a beautiful consequence of this, that E1 cannot be, well, arbitrarily large. You must have some degrees of freedom below some gap, which is a function of the central charge. And if E1 were higher, then it would contradict the Bootstrap equation. This is from a nice paper of Hellerman that utilizes the same philosophy of the Bootstrap of the previous paper by Rattazzi et al., but now in the context of the modular Bootstrap.
Okay. Can I ask a question?
Yes.
So your Z beta being equal to Z1 over beta, you assume there that the theory is defined on a torus, right? So you including the spatial dimension.
Yes.
What if it's not periodic in the spatial dimension? Do you still get similar constraints? Or?
No, in two-dimensional conformal field theory. Okay, so the idea is the following. So I'm considering, before continuing theory of finite temperature, I'm taking a theory in a cylinder. So there's a spatial circle, and then there's time that goes, is a vertical direction of the cylinder. And then by making time, Euclidean time periodic, I go to finite temperature. But actually, in 2 dimensions, the cylinder can be mapped to the plane by conformal transformation. So actually, no, the story is completely general. There's no assumption about periodicity in space. It's just the conformal transformation of the plane.
Thank you.
Okay, so great. Now we have this tool, and the game is to construct this clever function as I mentioned earlier and compute E1. And that can be done on a computer by linear optimization methods. And it can be done with great accuracy. And we found 2 absolute stunning surprises at these 2 special values dimensions of the conformal charge, the central charge, 4 and 12. And there's absolutely no reason why E1 or E2 or E3 should be integers, but that's what happens. at this value of the central charge, the optimal theory, the one which has the highest possible gap, appears to have, within extraordinary numerical accuracy, 10 to the minus 30, appears to have a spectrum that lies precisely at integer value of the dimensions. Not only the energies are integer, but the degeneracies. So the first excited state, E1, has energy 2 for C equal to L, for example, and has a degeneracy, which again, with extraordinary numerical accuracy, is a famous number, which is 196,884. There's this famous equation that is equal to 196,083 plus 1, where this number is the dimension of the smallest representation of the monster group. The monster group is the largest sporadic simple group. This equation had appeared before in math. It's a famous story related to this really beautiful and fancy subject of moonshine. And so we have a hint of something really magical happening. There's a hint of modular forms. This numerically determined thermal partition function happens to just be related to the modular J function. And this came from nowhere, because nowhere we assume that the spectrum had to be integer, nowhere we assume that the spectrum had to be, that the partition function had to be holomorphic, but somehow holomorphy and modularity emerge out of nowhere. So that's what happened. For C equal to 4, there's a similar miracle. And then what's also mostly interesting for the point of view of making contact with semi-classical gravity is to try to understand what happens for very large dimension. Here, by some numerical extrapolation, you find that the gap scales linearly with the central charge with a denominator which is something like 9. So it's a little below the black hole threshold. Okay, so of course, this is just a necessary condition. There could be other conditions that push this up to the black hole threshold, but that is the best we can do with this kind of method so far. Okay, so in the rest of the talk, I want to explain this miracle and, explain quote unquote. There's something clearly very intriguing going on here. It relates this three-dimensional gravity, which is also the same as the modular bootstrap, with some deep mathematics, and we would like to understand what that means.
Can I ask one question? The gap, the asymptotic gap for large central charge seems to be actually larger than the smallest mass of a black hole, right? Because it's C divided by 9 instead of C divided by 12.
That's what I meant. So indeed. So in this, sorry, I should have changed the picture. The picture earlier was yes, I'm sorry. I cut and paste the picture and that makes it confusing. So the previous picture was trying to see whether we had to find degrees of freedom below the black hole shell, and here we find actually that the up to what we can tell so far, we can actually overshoot the black hole threshold, and it's not guaranteed that we find degrees of freedom in the black hole threshold. So that is an indication that this bound is not optimal. Right. So the semi-classical gravity in the bulk is telling us that we should be able, in the fullness of time, to get a better bound on the gap and push it down to C equal to 12. Thank you. Okay, so now I'm gonna. So I've told you about two things so far. I told you about the bootstrap, especially the modular bootstrap, and I told you about quantum gravity, especially in 3 dimensions. And now I'm going to tell you about the third topic, which truly comes out of the blue, but bear with me. So I'm going to now switch gear completely and tell you about sphere packing. So this is a famous ancient question in pure mathematics. And it's the question of what is the densest configuration of identical non-overlapping spheres in the Euclidean dimensions. It's a very deep question which has connection to modular forms, lattices, number theory, cryptography, information theory such as error correcting codes, etc. And I'm now going to establish today yet new surprising connection to black holes. So the problem really appears to have a different character in each dimension. And no matter how many dimensions you study, the next one will have a surprise. It's only been solved in these dimensions. In one, of course, it's obvious, just intervals one next to the other give you a complete a density of 1. It's obvious to guess what the answer is in 2 dimensions. The best way to pack coins is to put them in hexagonal lattice like this. The proof is elementary, but actually it's a little subtle. It took till 1940 to have a rigorous argument. In 3 dimensions, if you think about it for a minute, there's no doubt again what the optimal answer is. You just take a hexagonal stack of spheres and you pack them, you pack one above the other. In fact, there are infinitely many inequivalent ways to do it, but they all give you the same density. And one way to do it is with the face center cubic lattice. But there are other. But if you translate the stacks a bit one with respect to the other, you can get non-periodic packings that have the same density. And this was originally asserted by Kepler. In fact, there's an interesting story of how all this came about. So Sir Walter Raleigh was this very colorful figure in England in the late 1500s. He was making war and commerce with the New World, and he wanted to have a formula for how many cannonballs he could put in a ship. So he asked a geographer and mathematician by the name of Thomas Harriot to calculate the formula, and of course he did. It's not hard. And Thomas Harriot was in correspondence with Kepler. They wrote each other several letters, and it got Kepler interested in the problem. And this stimulated Kepler's imagination, and he wrote this very interesting article on the in which he was trying to prove by this kind of methods based on discrete geometry, why is it that snowflakes have 6 corners? He didn't solve the problem, but you can see here from Kepler's paper, he was playing with stacking of spheres. He just asserted that this is the densest way to pack spheres in 3 dimensions. And this problem resisted proof for centuries. It was included by Hilbert in his famous list of problems, and was finally proved by Hales in 1998. The proof is extraordinarily hard. It's hundreds of pages. It uses computer-assisted methods. And it's also famous in the history of mathematics because it's one of the first difficult proofs that has been very recently completely verified by formal logic methods. So now there's a certificate that by formal logic methods that the proof is actually correct. And so it came actually as a big surprise, where in 2016 on Pi Day, Marina Wiazorska released a preprint archive. It's a paper of 10 pages or so, and she gave a beautiful, short, elegant proof that in 8 dimensions, the E8 Lord lattice is the answer. And the very same technique, a week later, with a few collaborators, they were able to prove that in 24 dimensions, the Leech lattice is the optimal pack. So, so what is the idea of the proof? So Wiazorska built on a previous approach from a few years earlier, 2006, I believe, by Kohn and Elkis. And hopefully this will now start ringing a bell. What Kohn and Elkis show is that if you exhibit a function f or r with certain positivity properties and also behaves in a certain way under Fourier transform, that proves an upper bound on the packing density in any given dimension. And it's hard to find this function, but you can, again, put it on a computer and find the best function in any given dimension by linear optimization. And so what is plotted here, the red curve is the Konelkis bound, which is obtained numerically. And you see it's a smooth curve as a function of the dimension D. And the best known packings are shown here as these blue dots. And you see it's a very jagged, irregular curve. There's no claim that these are necessarily the best packings. They are the best known ones. Presumably they're the best up to dimension 9 or so. The story becomes frustratingly hard in higher dimensions. So this is the upper bound on the density of the packing. One thing that you immediately notice that spheres do a terrible job at packing things in high dimension. You know, the packing density decreases exponentially in the dimension. So in high dimension, spheres pack an infinitesimal fraction of your whole space. And that's the upper bound. There's also a lower bound, and the lower bound has a different slope, and the upper and lower bound are separated by an exponential amount in the dimension D. And the truth is nobody absolutely has any remote idea of what is the behavior of the best packing in high dimensions. You see that the story is completely irregular, it's crazy. Some of these packings are lattice packings, some of it are periodic, but you know, with of the order of 100 different spheres in a unit cell, and it's actually believed that in sufficiently high dimension, the best packing is completely amorphous. There's no periodicity whatsoever. But a very curious feature of this plot is that, well, for dimension 1, it's sort of trivial, but in dimension 2, 8, and 24, the numerical bound exactly coincides, in fact, again, with the ridiculous numerical precision of e to the minus 29 or so, exactly coincide with the non-lattice packings. In 2 dimensions, hexagonal packing. In 8 dimension, the 8 packing, and in 24 dimensional Lich packing. In 3 dimension, curiously, the Hales result, which is this cannonball packing, is strictly below this bound, which is obviously telling you that the bound is a necessary condition, but you know, we know in 3 dimensions the problem has been solved, and you cannot do better than this dot here. Nevertheless, the Konelkis bound wouldn't reach it. And so this pretty much amounts to a numerical proof that was known before Wiazowska that the E8 and Lich lattice solved the problem. But, and so what Wiazowska did essentially was, by very clever answers that involve modular functions, she constructed analytically the Konelkis magic function and proved then that in 8 and 24 dimension, these are the best packings. Okay, so I told you this little tale, and now you may wonder, what does that all to do with anything? Well, perhaps you're already getting the hint, and that's the punchline. The punchline is that the sphere packing problem and the modular bootstrap are entirely equivalent to each other. So the Konelkis function that you can use to put upper bounds on sphere packing density is the same thing as the clever linear functional for the modular bootstrap. There's a bit of fine print here. The modular bootstrap, the version of the modular bootstrap that we're interested in for pure gravity is one where the symmetry is just Virasoro. Here we need to include vector bosons. You want vector bosons to make it fully equivalent, but essentially equivalent to the Konelkis problem if you include these additional vector bosons. And here's how the dictionary goes. The modular bootstrap with central charge C is related to the sphere packing in dimension D by this relation. And so these 2 cases where numerically we were finding these miracles, which were central charge 4 and central charge 12, are now quote unquote explained. What's the magic that is happening there, that they get related mathematically to the sphere packing in 8 and 24 dimension, which are these very special lattice structures, the E8 and Leech lattice. And you can also relate the packing density with the energy of the first excited level. And on the modular bootstrap side, or actually in a closely related version of the bootstrap, which is the one-dimensional bootstrap, Dalmil-Masac, in just around the same time that Wiatrowska proved her theorem, had proved optimality of this bound. And so there is an alternative history where physicists could have proven the packing story before the mathematicians if we had known about it. And it turns out that the magic function of Wiatrowska and the analytic function of Masac are mapped into one another. And so this is the very interesting implication that the question of finding the best minimalistic theory of pure gravity in 3 dimensions is closely related to the question of finding what is the most efficient packing of spheres in very harsh dimensions. Okay, so I have a couple of slides on something a little different, but I don't actually have to talk about it. The main part of my talk ends here, and so I can or cannot talk about those. So if there are any questions, perhaps ask them now.
Thank you. If it's under 5 minutes, it's fine to show these slides, of course.
Okay, so
we have one question already, though, Leonardo, from Eliezer.
Hi. Just to clarify some things. So when you talked about 3-dimensional gravity, did you consider it coupled in such a way that it's part of a string theory? So you're sure there is an ADS CFT part, or are you handling really 3-dimensional gravity on its own? That's the first question.
So I'm not making any assumption either than there is that the theory is in asymptotically 3-dimensional to the Sitter space. And so I'm using the DSFT correspondence as an axiom. I'm saying that any theory of gravity in 3-dimensional asymptotic and the Sitter space is by definition the same thing as a 2-dimensional unitary conformal field theory.
Okay, but are you making sure that from the point of view of string theory, the left side is a string theory, or you don't care about that?
No, I don't care. The part of the program is to precisely find whether string theory is necessary or not.
Okay, but then maybe
in 3 dimensions, the answer is we don't really know even in 3 dimensions, but you could borderline believe that in 3 dimensions you don't need string theory. In 4 dimensions, you'll be very surprised if something like pure gravity were a thing. In 3 dimensions, you know, the model is sort of topological, but not really. So perhaps pure gravity is consistent on its own. Okay,
so the assumption of the ADS of the 3-dimensional gravity equivalent to a CFT, it has an assumption part. But now
I would say that in the modern understanding of things, that is the definition of quantum gravity, right? You know, barring someone that will explain to us what quantum gravity is, I would say we have a perfectly good working definition for it in asymptotic and the Sitter space. Quantum gravity is a CFT with a large central charge.
Okay, but then my next question would be, if that 3-dimensional gravity has in it a Hawking-Page transition, and if you are sitting at temperatures below that, where do you see that? Because that would change your spectrum.
Yes, of course.
Well, not the spec, it would change how things look. So how would you see that? Where do you see that part?
Well, but we're studying the theory. We're imagining that we have this exact description of the Hilbert space. And so we're working in the microcanonical ensemble. We have the exact degeneracy and energy levels. And we can ask whether those are compatible with modular invariance. That's really what we're doing. So yes, you can, the semi-classical ball description will look different according to which regime you study it, but from the point of view of this abstract bootstrap problem, all there is this general constraints of positivity, modularity, etc. Okay, let me perhaps tell you very briefly. So we have this finite box, which was very instrumental for us getting precise results, but of course, we would like to remove it. And intuitively, of course, what we need to do is to send this curvature radius to infinity and think of this correlation function as in the process smoothly becoming the usual scattering of particles that we're familiar with in quantum field theory, just the standard S matrix. And of course, this connects with this even more ancient program of constraining S matrices that I alluded to that earlier when I was talking about the S matrix program for the strong interactions, which is to constrain something like 2-2 scattering as a function of the Mandelstam variables using time order assumptions, analyticity, crossing boundedness, which are supposed to encode things like such as unitarity and causality, but the details have never been fully spelled out. But the issue here is that whereas on the left-hand side, on the CFT side, we exactly know what we are doing, the bootstrap axioms are perfectly precise. As we attempt to take this flat space limit, we get into a bit of a more delicate story about what exactly we should require from the S matrix. But if we sort of proceed a little blindly and assume that all the good analyticity and boundedness properties which are implied by the error are true, then we can get real results. And this is an example from a recent paper with Simon Carignon, Damien Massage, and David Simonsdaffing, where you can sort of look at some little toy model, gravity coupled to a massless scalar, which has higher derivative interactions, and you can really put rigorous exclusion plots subject to those assumptions about how these couplings should behave in a perturbative regime where we take the Newton constant to be small, and the region on the right of this exclusion curves are allowed and the region on the left are excluded, and this is a story in various dimensions. And ideally, you like to do this for graviton scattering. That's hard because of the polarizations, but if you have maximal supersymmetry, you can effectively strip out the polarizations, and you can find this preliminary but still very, very suggestive results. So if you have maximal supersymmetry, you can easily prove that the leading correction to square root GR is R to the fourth. And in the limit, again, in the limit in which the model is perturbative, so you imagine you have a sequence of theory where G is going to 0, then this coupling G0 obeys a rigorous upper bound as a function of the UV cutoff, which is obeyed in string theory. Okay, so let me conclude. So I told you a story that involved essentially three, apart from the last few comments, essentially three characters. The conformal bootstrap is amplified here with its particularly simple version of the modular bootstrap. Black hole thermodynamics, especially in 2+1 dimension, and sphere packing. The question of what is the simplest theory of 3D gravity is still unanswered. We still haven't been able to either prove or disprove that we can reach this C/12 bound. And there is a very intriguing connection between pure gravity and the behavior of sphere packing in very high dimensions. Insights flow in both directions. In fact, our colleagues, both mathematicians and physicists, teamed up. And for the first time since the late 70s, they obtain, at least conjecturally, these are numerical results, an exponential improvement on the upper bound on the density of sphere packets in large dimension. This improves by a tiny bit, but it's a tiny bit in the exponent, a previous upper bound by Kabatansky and Levestein. And we just focus on a very specific, so it's not like a packing of sphere gets directly related to gravity. It's more like the bounds on both problems are the same. But there are, of course, many more constraints. Conformal field theories are rigid objects. They have many more equations apart from the modular invariance equation I emphasize, and sphere packings also have many more constraints than just the simple linear programming bound that I showed. And are there more general relations between the two? We don't know. And finally, I sketched a bit how we're at the beginning of this quantum gravitational arithmetics bootstrap, which we can play in flat space or in ADS. In ADS, it's more rigorous, and it's upcoming. Thank you very much.
Thank you. So now it's time for questions, especially from students.
Sergey has a question already.
Yep.
Yeah. So on the slides which you're showing the bounds from scattering, some of these Wilson coefficients, they have log running, right? So there's some implicit assumption here at the scale at which is bound are set, or
okay. So of course, this is just very quick. So what we are imagining doing here. So an example to where this would apply to is string theory for fixed but very small string coupling. So take the string coupling 10 to the -6, and big M would be the string scale, the scale of which the first massive string state appear. So in that situation, you have an effective field theory, which is still weakly coupled at scale big M. And so what I'm writing here is the effective field theory, where, yes, of course, you're right that in principle, there's a running of this coupling, but this running is tiny because the effective field theory is still weakly coupled with 10 to the -6 at scale big M. Eventually, the theory becomes strongly coupled, but at a much larger scale. Big M over some power of G string, which is the Planck scale. So these bounds are derived under this. So if I literally want to relate the Wilson coefficient of this effective action to this plot, then I work in the leading tree-level approximation, which is perfectly justified because the theory is weakly coupled at the cutoff scale big M. Of course, I could include loops, but those will make a very small difference for relating. The idea is that, truly speaking, the bounds here apply to some physical observable. These are bounds on some scattering process. To relate the strength of the scattering process with the Wilson coefficient, you have to do a matching, which here I'm just doing at tree level because I'm assuming that the theory is weakly coupled. Does that answer your question?
yeah, thanks.
Other questions?
By Eliezer and then Xuan.
Okay, I would like to ask you, because you said you want to do it modern. So there are also claims that lower dimensional theories of gravity are related from the point of view of this two-dimensional CFTs to averages over such theories, taking chunks of conformal space or the conformal manifold and integrating over them. And these are mathematical identities. So does this give you any further information? Can you use that?
Yeah, so the most standard version of the story is actually even in one-dimensional lower, is this claims about JT gravity, which is a bit two-dimensional gravity related to some matrix model. And there is a more recent version. I think you're referring to some papers by Maloney and Witten and Harman, Harman and collaborators about doing this in 2 dimension. And the story there is, it's a bit exotic. It's not quite gravity. You need to include a gigantic amount of vector bosons. And so the story there goes like this. You consider essentially toroidal conformal field theories which are free bosons and you look at the moduli space of toroidal compactifications. And if you integrate over the moduli space of Ravelli quantification, you get a simplification and you get some effective description to something that you might sort of call like gravity, but of course it's kind of an exotic theory of gravity in 3 dimensions. That's very beautiful. The significance of this for holography more generally are a little unclear to me. And I think nobody really knows the answer to this. I would be surprised, but I should be open-minded if something along those lines that appears to happen in JT gravity and perhaps in these more exotic examples in 2 dimensions really holds true in higher dimensions. We know, I mean, in 4 dimensions, we have this by
I'm
now.
just asking about 3 now.
Okay.
About 4.
In
Because
3,
you are 3 dimensions.
in 3 I could borderline. In 3, I can borderline believe it. So the question in 3 dimension, one possible scenario, which I think is plausible, is that what in the bulk you may want to call pure gravity, which is this theory of, so what would pure gravity look like? Well, you have the vacuum, then you have these little ripples, which are the Virasoro modes, the boundary gravitons. And then you start having only mass states of this very large gap, which case like C/12. Those are the black hole microstates. But more needs to happen. What really should happen is that you don't have, the states, first of all, should be non-degenerate and have a tiny separation, because we expect the theory to be chaotic. We expect something like eigenstate thermalization hypothesis to be true. So we expect this rather exotic behavior where we have, starting from the black hole threshold, we have this very large density, but with tiny separation of states and chaotic behavior of the energies and of the 3-point functions. Is there a CFT like that? Maybe, maybe not. What is the correct framework for doing this? A possibility, which I think is rather plausible, is that you will have a whole landscape of CFTs of this kind, although of course nobody has ever found one. And as you average over them, you will find a dual description in terms of just pure gravity. So just pure gravity, just Einstein gravity in the bulk with the cosmological constant could perhaps describe an average of chaotic CFTs of this kind. And then if that's the case, you would expect this average of theories which have these tiny separations to really give you a continuous spectrum. And so this is something that has been seen before. So there is this Maloney-Witten partition function that has a continuous spectrum starting from the threshold, but doesn't quite work because the degeneracy of states doesn't obey the correct positivity condition. Perhaps it can be fixed. So that is I think the direction in which the system papers are trying to go, trying to demonstrate that perhaps for pure gravity you could have a situation like that, where the bulk theory is really describing more like an average of chaotic CFTs, and then you have a continued positive degeneracy. One final comment, perhaps I'm telling you more words that you wanted to hear. It's embarrassing that people think that we know so much about 2-dimensional CFT theory, but we all know almost nothing. We do not have a single example of a conformal field theory that has anything like remotely behavior of what would be expected for such a thing. We do not have a sequence of conformal field theories whose with such a large gap. The moment you start to construct conformal field theory, inevitably you find a whole bunch of low-lying states. And so there's a little bit of tension. On the one hand, the gravitational picture suggests that there should be a ton of conformal field theory with this very large gap. But if you attempt to construct them by ordinary quantum field theory method, they're very, 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 very hard to construct. And the intuition here is the one that comes from the Wilsonian RG. You're asking for a theory which has a gigantic number of degrees of freedom, and essentially no low-lying states. I mean, how could you ever engineer that using anything like a Lagrangian or a lattice? The moment you have a gigantic number of degrees of freedom, of course, you're going to find a ton of low-lying operators. And so here we're asking for some really strongly coupled system that have a large number of degrees of freedom and a gigantic gap. That's very counterintuitive from the point of view of quantum field theory.
Thank you. So Joan has a question.
Hello. Yes, my question might be naive, but I want to understand, I mean, the purpose of the bootstrap problem. I never studied it before. So the idea is kind of, when you're saying you get the spectrum of gravity, in language of quantum field theory 1 would be to get the Lyman-Cullen representation for gravity. So the spectrum is really what the spectrum of quantum gravity. And the second question would be, if that spectrum of quantum gravity would be related.
Sound like a question, yes. Sound more like a statement.
What?
I did not. Your first question did not sound like a question.
If it is that, if it's what I have to have in mind, the real is.
Yes, absolutely. You have a precisely. Channel-Lehmann is appropriate word here because it has to do with not committing yourself to any specific microscopic model, but just citing general axiomatic property of the theory, such as the spectral representation. That is the spirit in which we're trying to do things.
Okay. And then should I think, for example, that each of those elements of the spectrum should be associated with one metric that I should sum in the path integral, and that would be considering all those metrics determined by those eigenvalues should be equal to the path integral of the CFT?
So that's a much harder question. So, and in some senses, the kind of question that here we're trying to sidestep. So we are looking at the system from this boundary perspective. And by looking at it from the perspective, on the one hand, we get the luxury of being able to be very precise. So we have a Hilbert space, we have states, we have operators. But then what actually goes on in the bulk, how do you recover the local bulk description, is kind of mysterious. And so in which sense, if any, something like a path integral sum over geometries in the bulk is going to reproduce this abstract data is hard. And that, of course, eventually what you like to understand, how, if and how the old ideas about Euclidean quantum gravity, or what kind of geometries are you supposed to sum in the bulk, what kind of topology are you supposed to sum in the bulk, can you even make sense of something like a sum over geometries in the bulk, and how that reproduces this data? That's hard. But in some sense, it's very interesting, but there really doesn't have to be an answer to that question. Here, the bootstrap approach has pros and cons. A con is that you don't get to really answer the question, but the pro is that perhaps you don't want to answer the question because you get into this conceptual morass that here is sidetracked. You're looking at stick with observables. The famous manifesto that Heisenberg wrote at the beginning of his famous paper on quantum mechanics. We wish to reformulate physics in terms of quantities which are in principle observable. That is the approach here.
Thank you. Glenys has a question.
Oh, also naive, I guess. But it's really very, very, very beautiful and inspiring. But what if can you imagine what sorts of insights it could tell you about 4 dimensions? Like, could you imagine being forced to have supersymmetry? Or, that's the closest thing I could imagine you might.
That is, of course, the question, right? So, of course, we're nowhere close to answering it, but indeed, so given that we're not going to have a Planck scale accelerator anytime soon, what are the constraints that we can try to put on low energy observables from UV?
But what I wanted to ask is, in the example you gave, you had this modularity, and there's no analog. Would there be for
there's
Or
no.
what would, how it might map to the more complicated 4D?
So that is the thing I was sort of getting to in the last part of the talk, which was a bit sketchy. This kind of thing here. So there are assumptions. This is not, unlike the ADS story, which was, you know, by the standards of theoretical physics, was, I would say, quite rigorous. The story here is less rigorous, but at least you can do something. And so here, the ambition here is, within a weakly coupled theory of gravity, what can you say about possible higher derivative corrections? And if you make certain, I would say, rather plausible physical assumption about how the S-matrix for graviton scattering should behave, then you can put bounds, numerical bounds on these higher derivative corrections. Of course, these are higher derivative corrections. So whether or not you'll be able to measure them experimentally is something that goes a little bit beyond my expertise, but perhaps you could. You could imagine that one day, I mean, not this very naive thing we were doing, but some version of it, some conceptually similar version of it, could put bounds on higher derivative counters. You could try to constrain in inflationary cosmology or whatnot. You know, presumably this is not the kind of thing that you can really measure with particle physics, but there could be cosmological signatures of this kind of couplings.
I assume that those are sort of reasonably more normalized, and from that perspective, they're not small. I mean, so it doesn't look like it's even very stringent. I mean, well, one is allowed.
I mean, you look at this plot. The point is, of course, here that what these bounds would give you are the relative strength of this higher derivative coupling. So if you had perfectly clever apparatus that you allow to measure all of them, then you plot them together and see whether or not you're inside these exclusion regions. That's the kind of thing you can imagine doing with current technology. Ideally, but you know, of course, I mean, I'm not trying to say I'm going to make any experimental prediction. That would be preposterous. But the kind of questions you can try to answer by these methods are a little bit more conceptual. Like, for example, we know that string theory solves the problem of finding a UV complete perturbative theory of gravity. Very legitimate question is string theory the only answer to this problem? Are there other perturbative theories of gravity that are not string theory? I think this is the kind of question you can really try to address with these methods. We know, for example, that graviton scattering, classical graviton scattering that obeys certain properties. We have general relativity, we have type 2 strings, we have type 1 strings. What else can you have? There's only very few models that are known, and can you classify perturbative theories of gravity? I think that's a reasonable question you can try to address by these methods.
Thank you. Other questions? I have one actually going back to conformal field theories. In 2 dimensions, there are also ugly conformal field theories like Liouville, and Liouville has periodically pops up as a failed attempt to be the dual of gravity. So how do they fit? How does Liouville or theories with a continuous spectrum and maybe without even a vacuum fit into this ADS?
Yeah, without a vacuum is a little problematic, but with a continuous spectrum, I saw sketch an answer earlier. So you could imagine that this is just a scenario, which I think is something that some people are willing to believe. One day our quantum field theory method will mature enough, we will discover this gigantic set of conformal field theories that have a large gap and this sort of tiny space spectrum starting from C of energy of order C over 12. And the spectrum will be sort of chaotic, and so each of them is kind of indistinguishable from one another. And then you average. And as you average, so conformal field theory really are healthy if the spectrum is discrete. But you could try to imagine that there is an effective description that comes from averaging And that description will have a continuous spectrum, and that average description is the one which is captured by semi-classical gravity potential. I think that's a plausible scenario. In 3 dimensions. In higher dimensions, I don't think so.
Thank you. We have other questions? So, well, maybe I want to ask a historical question. The first Bootstrap program fell flat on its back pretty hard, right? In the
Well,
so
actually,
what is new? I mean, what is new now?
It's interesting, you know, it's fun to look at those papers, and there were a lot of beautiful insights which are now being mined and, in fact, perhaps even plagiarized in the recent literature, because they're, of course, have been completely forgotten. What is new, I think, is 2 things. First of all, people were a little bit too ambitious. They wanted to find the unique theory of the strong interactions from first principles. Well, that's too much to ask. But now we have retreated to finding exclusion bounds. So, so I think that's more reasonable. And so I would be mildly optimistic that progress can be made. Something like large, I would say that, for example, a prime target for all of this would be large NQCD. Can you use these general principles to put constraints on large NQCD?
Thank you.
Actually, you may have partly answered the question I was going to ask, which was, I think all the examples, at least the ones that I focused in on well, were didn't have fermions. Is there a...
No, there's no conceptual difficulty in adding fermions, just for simplicity. Yeah, I mean, much of this story could be, in fact, supersymmetry usually helps. So you can certainly, in supersymmetry, there's no problem, or even with fermions, but without supersymmetry, yes, we can do fermions.
Let me see if I see other hands raised. I don't see any, so, but please do ask questions. We have already done some, but well, if none, we should thank again.
Thank you very much. It was fun.
Thank you, and we hope to see you in person for the next progress report of this when it will be possible. Thank you very much.